Rogério Rosenfeld, and together with Giovanni Villadoro from ICTP-Trieste and Gustavo Burdman from the Physics Institute at the University of São Paulo, and Joan Miró, also from ICTP-Trieste. So Gustavo and Joan will be here next week. We are the organizers of the 3rd edition of the joint ICTP-Trieste, ICTP-SAIFR School on Particle Physics. And I'd like to welcome you on behalf of the organizing committee. I'm sure you're going to have a fantastic experience here, not only because of the great lectures that we have, but also because you're going to meet each other and hopefully have bonds for the rest of your lives. I have bonds with, when I was a student, I have bonds with fellow participants of schools from the rest of my life. So this is, I hope it's going to be a good experience for you. We don't have much time for introduction now, but in the Q&A session, we're having more time to explain to you how things will work, and also I want to introduce, you guys introduce yourselves during the first Q&A today, so that we get to know each other a little better, and then we also explain how things will work, and of course we're flexible and things can change, so depending on your ideas. So the first set of lectures is Professor Christophe Grojean. Christophe did his PhD in Saclay. I won't tell you when. And he's an old friend, and he's a leader in the field of particle physics, and in particular this next collider that is going to be built at CERN, the future circular collider, which I heard is a terrible name, because once you build it, it's not future anymore. So I have to change the name at some point. And Christophe is going to give us, so all the lectures, we asked the lecturers to give on the blackboard, because we think it's a better way to learn. And please feel encouraged to ask questions, okay? And also, not only the Q&A, but also during the lectures, if you have any difficult, or if you want to know more about what is going on. So Christophe, okay. Oh, sorry, I forgot to say. So Christophe is a professor at DESY in Hamburg, sorry. And also the Humboldt University in Berlin. So Christophe, please.
Okay. So good morning, everybody. Good morning or good night, I don't know. It depends on which time zone you are. So I just landed this morning, so I may fall asleep during the lecture, right? Okay, good. So what Rogério didn't mention is actually what I'm supposed to talk about. So this means that I'm totally free, right? If I remember well, I should tell you a little bit about the standard model and what comes beyond, right? So we'll see how far we go, right? So again, Rogério said we should remain flexible. I remain flexible, surely. So also, don't hesitate to interrupt me at any time. And we'll start with basic stuff, maybe things that you have already heard many, many times, but doesn't matter. It's always good to hear it again, maybe with a different perspective. And we'll see where we will end up. So I will use a blackboard. I have also some collection of slides that I will make available for you later on, once I'm correcting, when all the typos will be corrected, right? Okay, so, yeah, standard model and beyond. Right? So we'll start actually with classical mechanics, because that's also part of the standard model. And we will start with a simple question, which is actually how far you can jump with a pole, with a wooden stick. So when I was a kid, I thought it's easy, just take a longer stick and you will jump higher and higher. Okay, I learned a little bit of physics, and clearly this doesn't work like that, right? It doesn't work like that because there is conservation of energy. So the higher you can jump is proportional actually to the faster you can run, right? So what happens is that you are converting your kinetic energy into gravitational energy, right? And this way you can easily find actually how high a human can jump, right? So you say simply that the energy is the kinetic energy, so that you should know, right? Classical kinetic energy. And that is supposed to be equal to G times the mass, right, of the guy that is jumping times delta H, right? And from there, you can easily conclude that delta H is equal to V squared divided by 2G. So little g is the gravitational interaction, right? So that's the only thing that you should know, gravitational acceleration, right? So first of all, I mean, it's interesting because, you know, it doesn't depend on the mass, right? So a fat guy can jump as high as a slim guy, right? So now you want to put numbers. So the fastest man on Earth is still Usain Bolt, right? Usain Bolt was able to reach the speed, I think, of 44, so V max, right? So it's Usain Bolt in Berlin, actually. What was the year? I don't remember. In 2009, right? He reached a speed of 44.72 kilometers per hour. Yeah. And if you convert that, right, I mean, with the right value of G that we are going to discuss in a moment, you see that delta H is 7.82 meters. Right? Which is not that far, actually, from the world record, right? I mean, I don't remember, it's 7 something, right? Or 690 something, right? I mean, so there is still room for improving, but the basic thing is that if everybody is jumping higher than that, means that he's cheating, right? He's violating the laws of physics. So now, clearly, I've used an interesting value, right, G, this gravitational acceleration, which is of the order of 10 meter second minus 2, right? So it's an acceleration, so it's the distance per divided by a time squared. So maybe, you know, you're on the beach. I mean, that happened quite often here in Brazil. So you're on the beach, and you want to compute, indeed, I mean, the world record of pole jump, but you don't remember the value of G, right? That happens, right? So 24 only? No. Okay, so there is still room for improvement. Okay, so what is this value of G? So how do you compute this gravitational interaction? So for that, acceleration. So you have to remember, for instance, this gravitational force between two bodies. This is G Newton, this fundamental constant of gravity, times m1, m2, divided by r squared, right? The distance between the two objects. And then m1 in this case will be the Earth, right? And m2 will be the guy who is jumping. So this you will write simply as G, this gravitational acceleration on the surface of the Earth, times m2, so the mass of the guy, right? So from there, clearly you deduce that G is G Newton, the mass of the Earth, don't remember, yeah, Earth is something like that, no? Divided by the radius of the Earth squared, right? So now, you didn't make much progress because you don't know those quantities, but at least this is a universal quantity that is the same everywhere in the universe, right? So you open the book, means you open my lecture notes, right? And this is equal to 6.67, 10 times 10 to minus 11. And now there is some units, which is m cubed, kilogram minus 1, second minus 2, right? So it's an acceleration. The mass of the Earth, that's something also that you should know, is 6 times 10 to the 24 kilogram. And the radius of the Earth, right? That's what I crossed last night, basically, from Frankfurt to Sao Paulo. And this 6,400 kilometers. Right? And then you put all the numbers. So this giving you 10 meter second minus 2, right? Okay, so, but you didn't make much progress because, again, I mean, this requires to know all these quantities, right? Which are not necessarily quantities that you are dealing with every day, right? But you remember also that Newton understood that actually, there is universality of the gravitational interaction. So this means that it's the same force that basically brings you the apple falling from the tree and the moon, orbiting around the Earth, right? So that's something that we can check also, that, you recover this value of the gravitational acceleration on Earth just by looking at the moon, at the motion of the moon. And that may be something that you remember, right? That the moon is actually orbiting around the Earth in something like 28 days, right? So the moon, 28 days. And the distance between the moon and Earth, I don't know, distance, moon, Earth, is about 1 second light, right? It takes about 1 second for the light to travel from the moon to the Earth, and I think it's 80,000 kilometers. Right? So now we want to compute really the acceleration of the moon, and from the acceleration, the gravitational interaction that is felt by the moon, and recover this value of g on Earth, right? So you say, well, it's an acceleration. So an acceleration is a distance, a time divided by a distance divided by time squared. So the distance is simply the orbiting of the orbit of the moon around the Earth. So 2 pi times this distance between moon and Earth, so times d, right? Divided by a time square. So you say 28 days squared, right? That is, well, so that's not the gravitational interaction on Earth, but that's the gravitational interaction that is felt by the moon. And then you have, of course, to rescale, because they are not at the same distance, right? So maybe it's g or g prime, let's say, right? So it turns out actually that this is not exactly what we need, because it's a circular motion, and for circular motion there is a factor 2 pi extra, right, which is simply coming from the Pythagoras theorem, right? So if you haven't never done this exercise, I mean, really look at this circular motion and recover this extra 2 pi that is really needed to make things consistent, and to be consistent between Newton and the guys jumping with a stick, right? Okay, so you put all the numbers and this will work. So this is the gravitational acceleration felt by the moon, and then this is simply g divided by the radius of the Earth, right? Divided by the distance between the moon and the Earth. Squared. Right, simply because the gravitational interaction scale like 1/r², so you need to rescale by this distance squared. And this again, from there, you will see that g is about 10 meter second minus 2, right? So that's really fantastic, right? I mean, you start with a simple question and you recover basically a lot of physics, right? A universality of gravitational interaction, conservation of energies. So if you understand this problem, you basically understand all the physics until basically quantum mechanics, right? Okay. So what is really fascinating here is this conservation of energy, right? And there have been some breakthrough, let's say, in the beginning of the 20th century that basically arrived to the conclusion that any kind of interaction is associated to some conservation or some symmetries, right? So the fact that the energy is conserved, right? E is conserved is simply because the laws of physics are invariant under time translation. Laws of physics are invariant under time translation. So there is a correspondence between the conservation and the symmetry. And that's basically the Noether theorem also that is telling you that every time you have a symmetry, you have a conservation of a quantity, right? So that's an example, let's say, of the Noether theorem, right? And then the next step was indeed to understand all the fundamental forces of nature as some symmetries. So yeah, there is an interaction because there is a symmetry, and there is a symmetry because something is actually conserved, right? So forces are associated to symmetries. And we are going to discuss what are the symmetries really of the standard model. So all the forces that exist among the building block of matter. So first of all, there are symmetries of space-time symmetry. So here we have seen, the invariance of the time translation that is associated to the conservation of energy. But there is also invariance on the space translation. So that's the conservation of the momentum, right? So these are space-time symmetries. And that actually corresponds to the Lorentz symmetry. So you want the laws of physics to be invariant under Lorentz transformation. So we'll come back in a moment. I will tell you a little bit more about those Lorentz transformations, right? How it works, how we understood really that, nature have to be invariant under this Lorentz transformation. And then there are other symmetries that we call internal symmetries that basically transform the various particles among each other, right? So the simplest example that you probably know all is the phases of the wave function of the electron, right? So the electron in quantum mechanics is described by a complex function, let's say. So there is a phase, and the phase somehow is unphysical, or you can change the phase in every point of space-time. So that's what we call a gauge symmetry. So there is a U1 symmetry. So U1 simply because you change one phase, so you change one angle. So that's really the symmetry of a cycle. That's what we call the U1, right? And this is nothing else than quantum electrodynamics. So the force associated to this symmetry is what we call electromagnetism. So it's QED, quantum electrodynamics. And it turns out actually that nature is a little bit more complicated than simply U1. And all the particles that we know actually have an internal symmetry, which is SU3 cross SU2 cross U1. So in a sense, you can really define the standard model as a collection of particles, right, which are invariant under Lorentz transformation and invariant under SU3 cross SU2 cross U1. So what I want to tell you in those lectures, I don't know, maybe today and tomorrow we'll finish, is really how did we understood actually there is this SU2 cross U1 symmetry. Right? SU3 is what is describing QCD, so the strong interaction. So that just explain how the different quarks combine together to form the proton and the neutron, or forming also some kaons, some mesons, etc. And then SU2 cross U1, so part of this U1 is actually this U1 of QED. It's not directly U1 of QED, it's a little bit more complicated via the X mechanism that we are going to describe. But there is this electromagnetism and the weak interaction. So the weak interaction is simply, the nuclear physics, the decays of big nuclei into other nuclei, right? So that's the purpose of today's and tomorrow's lecture, to really understand this SU2 cross U1 structure. Okay, good. Did I forget anything? No. So maybe I will spend a little bit of time discussing Lorentz transformations, or even though I'm sure you all know Lorentz transformation, but it's always good to remember how the different objects actually transform, because that will be very useful later on. Yeah, in particular in this first lecture, I would like you to understand most of the result just using dimensional analysis, you know. So Laura later on will tell you exactly how to do a precise computation, you know, with all this factor of pi, etc. But there are many things that you can understand just by looking at the dimension of the various objects. And for that, you need to understand how to build the basics, the basic blocks, so namely the Lagrangian. You know, you want to see the structure of the Lagrangian that describes the various particles. Okay, good. So Lorentz transformation is simply a transformation of coordinate, you know, for two observers that are moving with a constant speed with respect to each other, right? So you have a system of coordinate O with X, Y, and Z, and you have another system of coordinate, X prime, Y prime, Z prime, right? And the two systems of coordinate, I have even colors here, right? So there is a relative speed V0 between the two observers. So this is O prime. And the question is how the coordinates in the two systems are related to each other, right? So you have first the Galilean transformation, you know, that was what people thought to be true until basically Einstein comes along. And he say, well, the time is universal, so T prime is equal to T. And time flows exactly in the same way for all the system of coordinate. And then X prime here is simply V0 times T plus X, right? And then the other coordinate don't change. Z prime is equal to Z. Mm-hmm. So using this transformation, you know, you can easily compute what is the speed in the system of coordinate O prime, the speed of a particle compared from the speed in the first system of coordinate, right? Because V prime, so the speed in, let's say, in the system of coordinate O prime is simply dx prime divided by dt prime, but dx prime is simply V0, so V0 is just a constant. Right? The two observers are moving at a constant speed with each other. So what is here is simply dt plus dx divided by dt. Right? So this is quite easy. This is simply V0 plus dx divided by dt, and this is simply the speed in the original system of coordinate. Right? So here you easily, you know, recover what you all know, that the speed are just additive, right? But that's a problem, right? That's a problem because here, if the particle that you are interested in is a photon, so in the original system of coordinate is going at the speed of light, and then you add the relative motion of the two observers, and then you ended up into a photon that is moving faster than light in the other system of coordinate, right? And that's not what you observe, right? I mean, people have measured the speed of light, you know, in various ways, and they always find the same quantity, at least in the vacuum, right? So of course the vacuum never exists, but you know, it's just a limit, right? And this is not what they recover. So that's why basically Lorentz and Einstein, who understood it, I think, from the first principle point of view, came up with this new change of coordinate, right? And the big change is that time is not flowing universally, right? So T prime, so this is Galileo, right? And then there is Lorentz. That's probably something that you all know, but I mean, okay, we can spend some time, you know, discussing it again and again because it's so nice. So it's T prime is equal to T, no, I cannot read, minus V0 plus V0 divided by C times X. No? That's not what is written, but that should make it for the dimension, yes. And then X prime is X. Sorry, I forgot this gamma factor, of course. gamma 0. And here it's minus CT plus x gamma 0. Of course, I'm changing the notation compared to my notes, so it's probably wrong at some point, but doesn't matter. That's what keeps me awake, right? Otherwise, if I'm just copying what is on the note, I will fall asleep. So. Right. And now we can repeat again, the same exercise and compute the new speed in the new system of coordinate using this new transformation law. Right? So you want to compute v prime, which is dx prime divided by dt prime. So it's gamma 0 times c dt plus dx divided by gamma 0 times dt plus v0 divided by c times dx, right? So the gamma 0 cancelled. You divide everything by dt. So that's c plus dx divided by dt divided by 1 plus v0 dx divided by dt divided by c. Yes, that's it, right? So this means that it's simply v plus c divided by 1 plus v0 times v divided by c. So there is probably a c squared somewhere. Right, okay. There's a mistake somewhere, but okay. Just dimension, right? Okay. So here should be a c squared. Okay. And now, so the addition of velocities is a little bit more complicated, clearly. It's non-linear, right? So here it was certainly a linear dependence on v. So now v also appears in the dominator. But it has a property that if v is equal to c, then v prime is also equal to c. Right? You can check that immediately. It means that really the speed of light in this case is constant, right? Doesn't depend on the way you are looking at the photon. Right? So if v is equal to c, right, v prime is c plus c divided by 1 plus, we will fail? No. There is a mistake somewhere. Okay, doesn't matter. V0 times c divided by c squared. And that is supposed to be equal to 1. Okay, it's an exercise for you, yeah. Yeah, there is a V0 somewhere, yeah. Right. Next time I'll print a little bit bigger, right? Okay. There is V0 somewhere here, right? So it should be V0. Good. No? Yeah, okay. So let's put c equal 1, right? I tried to keep it, but clearly I failed, right? So I mean, you can put the c back with the dimension, and okay, good. So you correct that, and it's at the end of the day it works, right? So it's here it's v0, it's v0 plus c, right? Whatever, it's equal to v. It's equal to c. Sorry. Okay. Whatever you do it, it works. It's an easy computation, right? It means that it will fail badly when it will become more complicated. Okay, good. So Lorentz transformation. So basically we understood really that these are the important transformation law of space and time coordinates, right? When they are correct, clearly. So we want, all the quantities that we are going to write, we want to respect the symmetry of space-time. So now we know how the coordinates of space-time transform, but we still don't know exactly how the wave function of the various particles transform. Right? We need to know in which representation of the Lorentz group the particle belong. So mathematicians have tried to classify all possible representation, and those representations are actually classified by the spin of the particle. So there is a spin 0, the spin 1/2, the spin 1, etc., etc. Even though so far we haven't really found any particle of spin higher than 1, except maybe the graviton. There are still people that are discussing whether we have seen the graviton, whether gravity is really a quantum force of nature. But yeah, I think it has been well established that graviton exists, that it has a spin 2, right? We still haven't found a particle of spin 3/2. Maybe it exists. There are some theories that really predict that, for the theory to be consistent, you need a particle of spin 3/2, but we haven't seen any yet, right? Anyway, yeah, so the question is how the particle, right, transform under Lorentz transformation. And the simplest representation that we can imagine is actually the spin 0, a scalar field, right? Spin 0, which is a scalar field. And a scalar field is actually a field that doesn't transform, right? In the sense that phi prime of x prime should be equal to phi of x. Right. So there is no transformation of a scalar field. It's just an invariant under Lorentz transformation. So now the question is actually how do we write a Lagrangian that describes the dynamics of this scalar field that is invariant under Lorentz transformation? Right. So clearly, if the field doesn't transform, you can take any function of this field and it won't transform. So this means that the potential of a scalar field, right, the potential can be any arbitrary form, any arbitrary function, is automatically Lorentz invariant. V, so the potential of a scalar field is Lorentz invariant. But we also need to add the kinetic term in the Lagrangian, and we are going to see in a moment that d mu phi is actually a quantity which is invariant, and we will see that you exactly reproduce the classical equation of motion for a scalar field. So that's really a good candidate for the kinetic term. So let's say it's 1/2, and then you add minus phi. So that will be the general Lagrangian for a scalar field. So how do we check explicitly that this term is indeed Lorentz invariant? So we want to know how the derivative of a scalar field transform. So let's say a generic Lorentz transformation, right? So x mu going into x prime mu, right? So now that you are grown up, I will replace this system of coordinate by x mu directly, x mu. So mu equals 0 is just the time, right? Or c time, the product of the speed of light times the time, and then mu 1, 2, 3 is just the space coordinate, right? Okay. So x mu goes into x prime mu, which is lambda mu nu times x nu, and it's a Lorentz transformation. So you want, that's something I didn't explain, but you want the Lorentz distance to be invariant. So you want x mu eta mu nu, x nu times x nu to be invariant, so to be equal to x nu times x prime nu, right? So that's what defined a Lorentz transformation, right? So maybe something that I should have explained here that I didn't explain is that the quantity which is delta squared, which is ct squared minus x squared minus y squared minus z squared is actually invariant, right? So this is equal to delta prime squared, which is ct prime squared minus x prime squared minus y prime squared minus z prime squared, right? So it's a generalization of the rotation. The rotation leaves the spatial distance invariant under rotation, clearly. But here what you are doing is that you are doing a rotation that mixes space and time. And this quantity, which is the Lorentz distance, if you want, this quantity is invariant under this Lorentz transformation. So written in this formalism with x prime, x mu, simply telling you that eta mu nu times lambda mu mu prime, lambda nu nu prime is equal to eta mu prime nu prime, right? So that's what defines really a Lorentz transformation. Okay? And something that can be useful later on is actually to look at small Lorentz transformation. So when the Lorentz transformation is almost an identity times a small perturbation. In this case, you can linearize your equation. That's always easier. This is a nonlinear equation. There is the Lorentz transformation that appears squared here. But physics is always becoming simpler when you linearize everything. And that's, I think, the power of all these symmetries, property, etc. You can build a transformation by making several times a small transformation. That's the power of Lie transformation of the Lie group. You can exponentiate everything. Exponential of a small quantity is a large quantity, as we have learned in COVID, right? So if you say that lambda mu nu is close to identity, so delta mu nu, so that's equal to 1 if mu is equal to nu, plus a small perturbation, omega mu nu. So you can rewrite this equation. Yeah, okay. I didn't tell you what eta mu nu is, right? Assuming that that you already know a few things. Is 1 minus 1 minus 1 minus 1. Right? It's a diagonal matrix that differentiates the time from the space. And then this equation is simply becoming that omega mu nu plus omega nu mu is equal to 0. Right? So omega mu nu, when you lower the index with this matrix eta mu nu, becomes an antisymmetric matrix. So that's what defines a small Lorentz transformation. Okay, I wanted to tell you that this is a Lagrangian which is invariant on the Lorentz transformation, right? So we have seen that x mu goes into x prime mu. So now we want to see what it d mu. So this is d over dx mu, which is dx prime mu prime divided by dx mu times d over dx prime mu, right? Just the composition of the derivatives, right? And now you know that dx prime mu prime divided by x mu is simply lambda mu prime mu times d prime mu prime, right? So that's, you know the transformation law of the coordinate, and now we have derived the transformation law of the derivatives, right? So since phi prime of x prime is equal to phi of x, no, you want to take a derivative now. So d prime mu prime phi prime of x prime will be equal to lambda. Okay, let's do it in the other way, maybe. You want d mu phi of x. D mu will be lambda mu prime mu, d prime of mu prime, and phi of x is phi prime of x prime, right? Okay? And now you can simply look at the transformation d mu, so I will write explicitly this eta mu nu d mu phi d nu phi. So this is eta mu nu, eta lambda mu prime mu, lambda mu prime nu, d prime mu prime phi prime of x prime, d prime nu prime phi prime of x prime, right? And now you see that if I'm dealing with a Lorentz transformation, this quantity is nothing else than eta mu prime, right? So this is telling me that this quantity is d prime mu prime, phi prime, d prime mu prime of phi prime, right? So indeed, what I've shown here is that this Lagrangian here is indeed Lorentz invariant. Okay? So we are making steps. I mean, maybe I will write it down here because that's something that we will use later on. So spin zero particle. So spin zero. So Lagrangian is 1/2 d mu phi minus v of phi, right? Okay. By the way, from the Lagrangian, you can recover the equation of motion, you know, saying that the Lagrangian has to be extremal, and you recover the Klein-Gordon equation, basically. Right? We can do it later on if you want, right? Maybe this afternoon during the Q&A, right? Okay, so that was the simplest representation of the Lorentz symmetry, you know, the spin zero particle. In most of the particles in nature actually are not spin zero. They are spin 1/2. I mean, the electron, the proton, but the proton is not elementary particle, but the quarks are spin 1/2 particle. So they transform in a way which is slightly more complicated. And actually to derive, you know, the transformation law of the spin 1/2 particle it's a very beautiful exercise. It's a little bit technical, so here we'll only show you the result. And we will see what we can do with those results, right? So again, you know, spin 1/2 particle, right? So in this case, so this spin 1/2 particle is described actually not by a single function, by a set of functions that we call the spinors. So that's what Dirac, you know, constructed. And then psi prime, psi of x, right, that describe, again, this spin 1/2 particle, goes into psi prime of x prime, which in this case is identity. So this spinor lives in a space of 4 dimensions. So actually, particle is described by four different functions, and it transforms in this way, at least for small Lorentz transformation. So omega mu nu. Then you have the commutator of the Dirac matrices times psi of x, right? So what are these Dirac matrices? Well, these are the matrices that appears in the Dirac equation. So you know that the Dirac equation is what? Is I gamma mu d mu plus or minus m psi is equal to 0, right? So that's the Dirac equation. You have, again, you know, the spinors that live in a 4-dimensional space, and you have matrices here, gamma 0, gamma 1, gamma 2, and gamma 3, that are 4x4 matrices, and they satisfied a particular algebra, right? The anti-commutator of gamma mu with gamma nu is, I think, 2 times eta mu nu. Right? So you can try to build some 4x4 matrices that satisfy this, and you will find the Dirac matrices. So the Dirac matrices are not unique, but there is various representation of the Dirac matrices. So how did Dirac build this equation? Well, he was simply looking at an equation which is linear in the derivative, right? So single derivative, and an equation which is also compatible with the Klein-Gordon equation, right? And that's what he came up with. Right? So, as I say, I mean, this is really something which is non-trivial. I mean, you know, but this structure is really dictated by the group structure. You know, you want to do, you want basically the Dirac equation to be the same in every system of coordinates. So this is true for psi, but you want to have the same equation to be true also for psi prime with the same Dirac matrices. So the Dirac matrices, in a sense, are invariant under Lorentz transformation. And that, you know, requiring this invariance or covariance of the Dirac equation is basically enough to really find this unique transformation property, right? Okay. And yeah, so now the way to actually read this Dirac equation from a Lagrangian, again, you want to build a Lagrangian which is invariant under Lorentz transformation. And actually here it will be simply psi prime, gamma 0, I, gamma mu, d mu, minus m psi. Right? So you can check that this is, again, Lorentz invariance. So this is not totally trivial, you know, because, okay, psi transform in this complicated way. But at the end of the day, if you add this gamma 0 here, you can see that this is an invariant under Lorentz transformation. And clearly, to reproduce the Dirac equation, if you take the variation of this Lagrangian with respect to psi dagger, for instance, well, it's immediate that psi will satisfy this Dirac equation. Right? Okay? So that's the spin 1/2 particle. Psi dagger, gamma 0, I, gamma mu, d mu minus m, psi. Right? Okay, so at this point you are maybe lost, right? Because I've introduced this whatever Klein-Gordon equation, this Dirac equation, etc. And how do we know that those equations? I mean, how do you connect those equations to things that you know from, let's say, classical physics, right? Actually, those equations are nothing else than the quantum version of the usual relation between. Yes. That's much more complicated, right? Because, I mean, the field is not invariant under Lorentz transformation. So building something that is invariant under Lorentz transformation is getting more complicated. Yes. Yeah, you can add, I mean, in a sense, yes, this mass term, in a sense, is part of the potential, right? But there is not so many things that you can build. So, you know, for scalar field, you can write basically any kind of interaction that you want. For spin 1/2 is more complicated, clearly. You have to check by hand, you know, that what you're writing is invariant. But yeah, you can write interaction, for instance, 4 Fermi interaction, that will be invariant. So that's a new sort of potential that you can write, yes. And I mean, we are going to write an example later on. I mean, that's exactly what, in a sense, Fermi introduced to describe nuclear decay, right? Okay. Yes. No, I wanted just to make the connection, let's say, with between this Klein-Gordon equation or Dirac equation with classical physics. Right? Yeah. So the Schrödinger equation. The Schrödinger equation is not actually an equation which is invariant under Lorentz transformation, and that shouldn't be a surprise, right? Because the Schrödinger equation is simply, so Schrödinger equation is nothing else than the quantum version of the usual expression of the energy, right? Classical equation, so just p squared divided by 2m, the kinetic energy, plus the potential, right? So that's what you learn when you're doing Newtonian physics, right? So how do we go, let's say, from classical to quantum version? Well, you simply replace the energy by the time derivative, so I h bar d over dt, and you replace the momentum by I h bar d over dx, right? So in this case, it gives me what? I h bar d over dt, so that's the energy. It applies to the equation of motion. Then it's p squared, so you need to take the squared, so it's minus because there is I. Then you flip in the other side, so it's plus h bar divided by 2m. Then the second derivative, so delta, the D'Alembertian, whatever, minus v applied to the wave function, which is equal to 0, right? Right, so the Schrödinger equation is nothing else than the usual expression of the energy in classical physics, right? Now, Klein-Gordon equation is the same thing, except that now you need to start with the expression of energy, which is the one which is invariant under Lorentz transformation, right? So it's just Einstein equation. So E squared divided by C squared is P squared plus M squared C squared, right? And I think I put the C correctly here, just to have an equation which is consistent with the dimension. And then you are using the same correspondence between classical physics and quantum mechanics, and then giving you 1 over C squared, the second derivative with respect to the time, minus delta plus M squared C squared divided by H bar squared applied to the wave function, which is equal to 0. So that's the simplest example. Yeah, I mean, you can replace the mass term by the derivative of the potential if you want, right? So it's V prime, whatever V prime, right? It's a derivative of the potential with respect to the field, right? And then the Dirac equation is simply the square root of this equation. So when you take the Dirac equation, in a sense, is the square root. So here E will be equal to plus or minus the square root of P squared C squared plus M squared C to the 4th. Right? And here, clearly, when you take the square root, there is a plus and the minus solution, and the minus solution has been interpreted as Dirac as actually antimatter, right? So just by looking at an equation somehow that is linear in the derivative, Dirac predicted that antimatter exists, and a few years later, indeed, the anti-electron was discovered in the cosmic rays, right? The positron by Anderson. So that's, I think, a fantastic example, of writing something which is consistent with the symmetries somehow, force you to discover something. So here, the combination of special relativity and quantum mechanics basically led to the prediction of antimatter. When you combine special relativity with quantum mechanics, necessarily you need antimatter for the theory to be consistent. Okay. So these are the building blocks. Well, there is one more thing that we need to introduce in principle is the spin 1 particle, right? And I will stop here. I won't discuss the spin 2. Spin 2 is, is gravity, is general relativity, and it's slightly more complex also to make it consistent really with quantum mechanics. Right? Yes. So how do we introduce the spin 1? What do I want to tell you? Yeah, maybe. To really understand the easiest way to understand the spin 1 is to look at gauge transformation. So I told you already that, if you want to describe the electron, for instance, you have the wave function, and, you want to change basically the phase of the electron in a local way. So local way means that I want to change the phase differently in different points of space-time. Right? So that's what is called a local symmetry or gauge symmetry. And yeah, you want a Lagrangian that is invariant under this kind of transformation, under this kind of local transformation. And this is possible only if you introduce another object, which is a spin 1 particle. Okay? So how do we see that? Well, just imagine for a moment that the electron is actually a spin zero particle, right? So I will do scalar, what is called scalar QED. It's easier to introduce the gauge field, and then you can generalize it very easily also for spin 1 half electron. But, so a phi, phi of x, that under this transformation will go into exponential I theta phi of x, right? And there are two different symmetries that you can consider. There are some global symmetries. So theta is independent of space-time. And there is local symmetries. So theta is now a function of x. And I want to build a Lagrangian which will remain invariant under those local transformations. So that was, so here that was a real scalar field in a sense, right? Now you can introduce a complex scalar field, so you just introduce a dagger here, a complex conjugate, and you remove this 1 half. And maybe here, instead of function of phi, it will be a function of phi modulus squared, right? So in such a way that this spin zero Lagrangian is automatically invariant under the global transformation, right? Because under the global transformation, in this case, d mu of phi goes into exponential I theta d mu of phi, right? So since theta is independent of space-time, when you take a derivative, the derivative doesn't act on theta. And now it's obvious that this remains invariant, right? So this Lagrangian is automatically invariant under the global phase transformation. But this is not the case for the local one, right? This guy, d mu phi, goes into I d mu theta, exponential I theta phi of x, plus exponential I theta d mu phi of x, right? And now you see that this quantity is not invariant any longer, right? You have this piece that depends on d mu of theta that remains. So this Lagrangian is not invariant under the local transformation, the local transformation of the phase. So the idea now, in order to construct a Lagrangian which is invariant under this local transformation, is to replace the space-time derivative by a covariant derivative. So you say that d mu phi will be d mu phi plus I. Probably I should put a gauge coupling at some point, but okay, we'll do it later. A mu of phi. Yes. And now I want to introduce a new field, A mu, that will later on be identified with the electromagnetic field, with the photon. And I want to tell you how this field A mu transforms in order for the Lagrangian to be invariant when I replace the derivative with the covariant derivative. So I will have A mu, A mu of x, that goes into A prime mu of x prime, which is equal to something, and this something is found in such a way that this Lagrangian is invariant under the local gauge transformation. Is it clear? Right, so you see, right, the principle is really to construct transformation laws in such a way that I find some object, the Lagrangian, which is invariant under all the symmetries that I like, right? So the Lorentz transformation, and then now some internal transformation. So this is called internal transformation because it really transforms the various particles among each other, right? So it's acting into the internal space of the of the collection of the particles. So here it's an easy, in the sense that the transformation in a particle space is just diagonal, right? It transforms a particle into itself. It just changes the phase of this particle. But later on, we will see some example where you have various particles, and the various particles will be transforming into each other. So the electron will become a neutrino, for instance, right? Okay. So how am I doing with time, actually? I know I've lost track. Half an hour, okay. So maybe we'll have some time to do some real computation at the end. Yes. Okay, so d mu of phi. So it goes into d mu of phi prime plus I a prime mu times phi prime, right? So I already know what d mu of phi prime is, right? So we'll factorize I theta. It's I d mu of theta times phi. Okay. We'll factorize phi also, plus I a prime mu. And that's it, plus d mu of phi, right? D mu of phi here. Okay? And yes. So now you see that if you identify that with I a mu, right? So if you choose a prime in such a way that this quantity is equal to I a mu, then this Lagrangian, d mu phi dagger, phi complex conjugate, d mu phi, will be invariant, right? Will go into itself. So go into itself, yeah. Same. It's clear because now I really factorize this, this exponential, right? So the equation that defines really the transformation property of the spin 1 particle is just that A prime mu plus d mu theta should be equal to A mu. So in a sense, I mean, the photon field or the electromagnetic field, you know, keep track, I mean, is the memory of how the scalar field transforms from one point of space-time to another. Right? It's just a memory. Theta, yes, theta, sorry. Right. So it's independent, yeah, of course it's important that it's independent of the field phi, right? It only depends on the transformation of the field. Okay. Good. So now I have introduced a new field, so I need to introduce some kinetic energy, let's say, associated to the field, right? So what is the kinetic energy? What is the Lagrangian that describes the dynamics of this field, right? It's a field which is propagating, so it's a new degrees of freedom, and you need to add a kinetic piece for this degrees of freedom in your Lagrangian. So again, you want to write something which is invariant on the Lorentz transformation. So A mu, you know, is an index, space-time index mu. So we will transform like the derivative, like d mu, and it's easy to see actually that this quantity is actually invariant on both the Lorentz transformation and the local gauge transformation. So L minus 1/4 f mu nu, where f mu nu is a field strength derivative. So it's d mu a nu minus d nu a mu. D nu a mu. Okay, so the Lorentz invariance is easy, is exactly like showing that d mu phi is invariant on the Lorentz transformation. Here it works exactly the same way, you know, using the definition of the Lorentz transformation, you know, the fact that lambda mu nu, lambda whatever mu prime, nu prime times eta mu nu is eta mu prime nu prime is enough to show that this is invariant on the Lorentz transformation. So now the last thing that we need to check is that this quantity is indeed invariant under this kind of transformation, under the Lorentz, under the gauge transformation. Right? And that's easy, right? Because f prime mu nu will be d mu a prime nu minus d nu a prime mu. And we know this is d mu of a prime nu, which is a nu minus d nu of theta, minus d nu of a mu minus d mu of theta. Right? So you have here d mu a nu minus d nu a mu. So this is f mu nu. And here you have d nu theta minus d mu of theta. And this is equal to 0 because the space-time derivative commute with each other. So here, this cancels with that. So in this case, the field strength itself is actually invariant under the gauge transformation. So clearly, if you take the squared, it's also invariant. Right? Yes? Yeah, that's the kinetic energy associated to the propagation of. Well, this 1/4 is just a normalization. Is basically to recover Lorentz, the Maxwell equation. Yeah, Maxwell equation. So the way. So you take this Lagrangian. You take the variation of the Lagrangian that gives you the classical equation of motion, and that's exactly this Maxwell equation. So this 1/4 is convention to be consistent with what you have learned from electromagnetism, right? To give you a simple identification, let's say, of this field A mu with the scalar and vector potential of electromagnetism. But yeah, it's pure convention. I mean, maybe different people will use different normalization. Sometimes there are even people that put the gauge coupling of the electric charge, which is a gauge coupling of U1 of electromagnetism here. So it's just normalization, it's convention, right? Okay? Good. So the Lagrangian, so spin 1. So tomorrow we'll see a generalization of this gauge transformation. So here, this is a gauge transformation that we call abelian, because you can perform two of those transformations in whatever order you like, and you get the same result. This is not the case when you are doing rotation. Rotation don't commute with each other. So that's an example of non-abelian interaction, and we will see that nature is also described by non-abelian gauge symmetries. So we'll need a generalization of that. In particular, here, in this transformation law of the spin 1 field, there will be something which is a little bit more complicated, and also in the expression of the field strength. There will be another piece that involves some commutator of the gauge field. But that's for tomorrow. So here it's still minus 1/4 f mu nu, f mu nu. You may ask whether we introduce a potential for the gauge field. Well, that's not a good idea. It will be very difficult. I mean, probably you can do it, in some non-perturbative physics, but to describe electromagnetism, there is no potential here. Okay. Yes. So why did I spend so much time actually constructing those Lagrangians? Is that now we can easily do some interesting physics with this Lagrangian. In particular, we can try to compute, I don't know, the lifetime of the proton or the lifetime of the neutron. Proton will be more difficult, and the neutron or the muons, right? So that's the Fermi theory, basically. That introduces indeed 4 Fermi interactions, so a local contact interaction among 4 particles, right? So what are those Fermi beta decay, right? So here it's what is called beta decay. So it's basically radioactivity, right? So there are some big nuclei that decay into other nuclei. So for instance, here, okay, there is potassium, 40, and now, I don't know, 19, yes, 19. So here is the number of proton, and here is the number of proton plus neutron, right? If I remember correctly, chemistry. And that goes into calcium plus, and that's 20 and 40 plus. So that's what people observe, right? So some big nuclei that decay into other nuclei plus an electron. There is copper, whatever, various examples like that. I mean, there is a long list, right? And here should be 29, I think. 29, I cannot read, 64. Goes into zinc, Zn plus, so 30, 64 plus electron. Or there is also hydrogen, right? Hydrogen with extra neutron, 3, goes into helium plus, 2, 3, plus electron, right? So that's, what was observed, I mean, in the early 19-something, right? And then what was more interesting is to look actually at the spectrum of the electron that you obtain. Right? So people were, looking at those decays and trying to measure the energy of the electron that is produced here. They do something like that, a plot as a function of the energy. And here they report the number of events that they see, right? And they obtain a plot that looks like this, right? And that's very, very strange, right? It's very strange because here you have, a particle that decays into two particles. And in this two-body decay, the energy or the momentum of the daughter particle, so the energy and the momentum of the electron, energy and momentum of the other nuclei, is actually totally fixed in terms of the mass of all the particles, right? Why is that? I mean, here, for instance, you have those particles. You can go into the rest frame of this particle. So the big nuclei is at rest, doesn't move. So it decays into two particles. So momentum conservation is telling you that the two daughter particles will have opposite and equal momentum, right? And then you simply write conservation of the energy, right? So the energy of the two particles here, the sum of the energy of the two particles should be equal to the mass of the mother particle, right? And this is telling you that basically, yes, the energy and the momentum of the daughter particle is uniquely fixed, by kinematics, right? Doesn't matter what are the interaction which is responsible for the decay, right? It's just conservation of energy and momentum plus special relativity, right? Because I've been into the rest frame of the particle is at rest, right? So I'm using special relativity, but it's telling you that if I'm using special relativity and conservation of energy and momentum, then what I should observe is that the energy of the electron should be like that. It should be a delta function, right? It should be uniquely fixed, and you can easily compute the energy here in terms of the mass of the mother nuclei and the mass of this daughter nuclei and the mass of the electron, right? But that's what you should observe, right? Something that should be fixed. And here, when you're doing the experiment, I mean, the endpoint here is close to what was predicted theoretically, right? Not exactly equal, it's slightly on the left, but okay, almost equal. So people were really puzzled about that, right? Even Bohr, say, well, it's quantum mechanics. Quantum mechanics, there is no conservation of energy and momentum, so you shouldn't worry, right? And then basically the solution to this problem, was proposed by Pauli. Say, well, wait a minute. I mean, who is telling me that actually there is not a third particle in this decay, right? A particle that I don't see, it's invisible, let's say, but is there. It carries energy and momentum. So we call this particle actually a neutrino. So nowadays we know that it's an anti-electron neutrino. Right? So that's exactly actually what happens, right? In those decay, there is actually here, it's a neutron that transforms into a proton plus an electron plus an antineutrino. So that's basic principle behind this nuclear decay, right? Is neutron going to a proton plus electron plus antineutrino electron, right? So I put it in parentheses because that was an hypothesis, right? I mean, that was just a theoretical idea of Pauli. Say, well, for my theory to be consistent with conservation on energy and momentum, I need to introduce a new particle. And it took some time, actually, for people to observe this extra particle, because indeed it's very difficult to see them. It has very weak interaction. So it escapes very easily your detector. But clearly, one proof that the particle exists is really this conservation of energy and momentum. I can tell you a little bit more, if you want, later about the history of this neutrino discovery. But we won't enter into the details now, because I want to finish with writing, actually, dynamics that describe really this decay, right? So as I told you here, I just use conservation of energy and momentum. So it's just pure kinematics. Now I would like to introduce some dynamics, right? I would like to introduce a force which explains why this decay occurs, right? And that's what Fermi proposed I think in 1928, I think, or something, no, 1933. He writes the first Lagrangian that actually describe this decay. He said, well, look, I have a process, a physical process, where a particle decays into three particles. So we'll write simply a contact interaction among those particles. Right? So in my Lagrangian, in addition to the kinetic term, I want to write something like that. Right? I want something which is certainly Lorentz invariant. So we'll write, okay, maybe a proton here, gamma mu. Well, let's forget about the gamma mu for now, for a moment. It's just a contact interaction among those particles. So nu bar E. Right? And no, it doesn't work with electric charge. It should be E bar nu. Right? So, so simply a contact interaction among the four particles that are involved. Right? And now I put a constant in front of it, G Fermi, right? That measure, let's say, the strength of this interaction. Okay? And now there is something interesting. That's where we are going to use actually a dimensional analysis, right? I want to say that in order for the data to be, for the theory to be consistent with experimental data, we will see that all these particles here have to be spin 1/2 particle. They are not spin 0 particle. Right? So what's the difference, right? I mean, let's do the two different computations. So let's assume that all these particles are spin 0. Right? So here I have 4 scalar fields. What is the dimension of a scalar field? Right? So what is the mass dimension of a scalar field? Well, so the Lagrangian needs to be of mass dimension 4. Right? Yeah, didn't explain this notion of mass dimension. Okay, so the action at the end of the day, the thing that you want to extract is just the integral over space-time, so d for x of the Lagrangian, right? In such a way that the probability of a phenomena to occur is always exponential of s divided by h bar, right? And I'm working in a system of units where h bar is equal to 1, like C, right? So h bar is equal to 1, so S is dimensionless. So it means that the Lagrangian is mass dimension 4, right? So yes, so h bar equals C equal 1 means that the distance has the same dimension as the time. which is the inverse of a mass. Right? So you can measure everything in electron volt or whatever, and then you reintroduce the right unit by the appropriate power of h bar on c. So this means that here, the Lagrangian need to be a dimension, a mass to the fourth. Right? So the dimension of the Lagrangian in mass is equal to 4. Right? Because this is -4, so -4 times 4 is equal to 0. So that's the right mass dimension for the action, and everything is fine. So the mass dimension of a Lagrangian is equal to 4, and here you have two derivatives and two power of the scalar field. It means that the mass dimension of a scalar field is equal to 1. Right? While the mass dimension of a fermion, right, here you have a single derivative. That was really what Dirac wanted, right? He wanted to write a Lagrangian which is linear in the derivative. Right? So now it's 1, so the mass dimension of a fermion is 3/2. So that's basically the only difference, fundamental difference between scalars and fermions. So I spent a lot of time constructing the Lagrangian, but at the end of the day, that's what I needed, right? I needed to understand why the mass dimension of a scalar is 1 and the mass dimension of a fermion, or spin 1/2, is 3/2. That's the basic difference, right? So now let's look at this Lagrangian, this Fermi Lagrangian, right? So this need to be mass dimension 4, right? Again, you add pieces in the Lagrangian, but the mass dimension of the Lagrangian should remain equal to 4. So in case of a spin 0, each of those field here is mass dimension 1. So it has already the right dimension. So G Fermi is mass dimension 0. G Fermi is equal to 0. Mass dimension is equal to 0. In case of spin 1/2, right, assuming that all these particles are spin 1/2, then it's 3/2, 3/2, 3/2, 3/2, so it's 6. So it means that G Fermi has a mass dimension -2. Right? So now let's try to compute, I don't know, a width, right? The width or the lifetime of the particle. So the lifetime is the inverse of the width, right? I mean, again, mass is inversely proportional to time. So it means that here the width of the neutron, right? Okay, width of the neutron. So mass dimension of this object is 1, right? It's a width, so it's the inverse of a time. So it should be 1. And we know, I mean, from quantum mechanics, that the width, it's amplitude squared, so it should be proportional to G Fermi squared, right? That an interaction is 1 power, and then so that gives you the amplitude, and then you need to square the amplitude to obtain, I don't know, cross section or width or whatever, right? That's just quantum mechanics. So now let's look at the dimension, right? So this should be mass dimension 1. So in case of spin 0, so G Fermi is 0. So it means that for the spin 0 particles, for the spin 0 hypothesis, here the decay width of the neutron should be 1 power of the mass. Okay, we'll figure it out later what the mass will put, but it's 1 power of the mass, right? For the case of spin 1/2 particle, G Fermi is -2, so it's -4, and it should get 1. So in this case, it should be G Fermi squared times the mass to the 5th, right? So I get two different predictions for the lifetime of the neutron under the two different scenarios, right? Spin 0 or spin 1/2. Okay, so now what is this mass or energy which is available in this decay, right? Well, the mass of the neutron is about 1 GeV. The mass of the proton is about 1 GeV. This is 500 kilo electron volts, so this is negligible, whatever. The mass of the neutrino, I don't know it, but it's very small again. So M, actually, in this case, for the neutron, right, for the neutron decay, m should be actually the mass difference between the neutron and the proton, right? They are almost equal, not exactly equal, but the neutron is heavier than the proton. That's a big question, actually. Why the neutron is heavier than the proton? I'll discuss that later in the lectures. But, so that's really the energy which is at your disposal, right? So from there, you can compute G Fermi if you want, I mean, under these two hypotheses. Now there is a very similar process, which is actually the decay of the muon. So I haven't introduced the muon, but I'm sure you have heard about the muon, right? The muon is very similar to the electron, except that it's heavier. So the muon is also an unstable particle. It decays into electron, plus antineutrino electron, plus muon neutrino. And we can maybe dream, and say that this is exactly the same kind of interaction, so the same force which is responsible for the two decay. So when I say it's the same force, I mean it's the same constant coupling constant that appears, right? So we'll use exactly the same expression now for the muon. The mass scale that I should put that is available is in the sense the difference of the mass of the muon, the mass of the electron, etc. But this is negligible compared to the mass of the muon. So in this case, m is simply the mass of the muon, right? Which is about 100 of MeV, right? 140? Yeah, 100, maybe forget. Okay. And from there, you can see that actually the ratio, so, I mean, there is one, let's say, I have, on the spin zero hypothesis, I have one unknown, which is G Fermi, and I have two measurements, the decay lifetime of the neutron and decay lifetime of the muon. So I have one prediction, one theoretical prediction, right? And the same, I have another theoretical prediction in the case of a spin 1/2 particle. Right? Is it clear? Yeah, maybe it's not clear. Right, so I don't know. Spin zero hypothesis, let's say. So you want to throw away G Fermi. So you say that lifetime of the neutron is G Fermi squared times mass of the neutron minus mass of the proton. And the decay lifetime of the muon is G Fermi squared times mass of the muon, right? And now you take the ratio. You obtain that the lifetime of the neutron divided by the lifetime of the muon should be equal to the mass of the neutron, mass of the proton divided by the mass of the muon, right? And now you open, I don't know, the particle data book, whatever, you find the experimental value for these quantities. So lifetime of the neutron is about 15 minutes minus 1, right? So this is 15 minutes minus 1. The mass of the lifetime of the muon is 10 to minus 6 seconds. Whatever, double prime. The mass of the proton. So now you need to look at the mass of the proton, the mass of the neutron. Where is it? Did I have it here? Yeah. Is 930. So the mass of the proton is 938 MeV. The mass of the neutron is 939 MeV. And the mass of the muon is 100 MeV, right? 130, 140. Right. Anyway, you do the math and doesn't agree at all, right? I mean, okay, it's 10 order of magnitude wrong. So clearly, this spin zero particle is not consistent with the experimental measurement. Right? Under the hypothesis that you like, I mean, here I've made a big hypothesis, right? That is the same dynamics which is responsible both for the decay of the neutron and the decay of muon, right? So physicists, I mean, they like, you know, to connect things that seems to be totally different. I mean, they seem totally different because here, again, the lifetime is 15 minutes. Here is 10 to minus 6 seconds, right? So nobody, you know, on Earth will tell you this is the same thing, this is the same dynamics. But, you know, physicists like to connect things that seems to be totally different, right? And indeed, you know, if you repeat the same exercise for the spin 1/2 hypothesis, now I know that lifetime of the neutron is G Fermi squared, Mn minus Mp to the fifth, right? That's really the important thing, right? This is power fifth, right? That's really coming from, you know, basic principles, the mass dimension, right? It's something that you cannot mess up with, right? And now muon is G Fermi squared, mass of the muon to the fifth, right? So now the prediction is what? Is the decay width of the neutron divided by the decay width of the muon is Mn minus Mp to the fifth divided by the mass of the muon to the fifth, right? So now you see the big difference is the fifth power here. And that's exactly this 10 order of magnitude that I was missing, right? Because here it's 1 MeV divided by 100 over MeV. And here is, again, 1 over 100 to the fifth power, right? So it's 10 order of magnitude. This 10 order of magnitude is nothing else than this power fifth that I introduced, which is coming from the mass dimension. So here I'm happy, right? I'm happy because I understood the data, right? I understood this data with very simple hypotheses that have the same dynamics, the same interaction, which is responsible both for the decay of the proton, decay of the neutron, and the decay of the muon. That's not the end of the story, of course. There is all the construction of the weak interaction in terms of this 4 Fermi interaction. So that's what I'm going to tell you tomorrow. How do we see actually this 4 Fermi interaction as secretly a gauge interaction, right? So generalization of electromagnetism. So instead of, you know, having a U1 symmetry, here it will be SU2 symmetry. An SU2 symmetry which will transform, in a sense, the electron into the neutrino, or we will transform, if you want, the neutron into a proton, right? So again, it's an example of a symmetry, you know, which is very bizarre, right? I mean, nobody on Earth will tell you that the electron should be identical to the neutrino, except, I mean, maybe Glashow, you know, that came up with this idea. Well, maybe nature is actually invariant when I really transform an electron into neutrino, and that's indeed a fundamental symmetry of nature. So again, you know, you should look at things that seems different, but actually they are the same, you know, when you really understand what is going on. Okay, so we'll stop here for today. Thanks.
Okay, so we have time for a few questions for Christophe. Of course, we have time for the Q&A session as well.
Hello, it was a very nice lecture. I have a question come back to gauge transformations. So when you are on classical electrodynamics, gauge transformations occur when you consider that the physical fields are the electric and the magnetic fields, so the potential can change by a shift. And in quantum mechanics, the idea is the physical observable is the probability density. So, so you can put a phase that's because the square module, that's the physical quantity you observe. So my question is, when you think in quantum field theory in general, there is some similar physical interpretation, or gauge transformations are just a way to put interactions in the theory? Thank you.
Yeah, I mean, you're asking basically whether gauge transformation are really physical transformation. In a sense, they are transformation under quantities that are not physical, because, as you say, they are the potential, in a sense. I mean, A mu correspond to the scalar potential and the vector potential, and these are not physical quantities, right? What is physical quantities, as you say, is the electric field and the magnetic field, even though, again, you know, you can transform each other under Lorentz transformation. Right, so whether, you know, the electric and magnetic field are physical, again, it depends also on the observer, right? Because they transform into each other under Lorentz transformation. But yeah, to come back to your question, so we introduce some symmetries under some quantities that are not directly physical. Mu is not a physical quantity. You introduce those quantities because, yeah, you have a very simple transformation of those quantities. So, you make some symmetries manifest if you are using the right system of coordinate in a sense, right? And that's the thing that you will also quantize. I mean, you know exactly how to quantize the gauge field directly from mu. It will be much more difficult, to come up with a quantization in terms of the electric and magnetic field directly. So it's easier to use this quantity mu. But yeah, I mean, X and Y are maybe not physical either, right? I mean, but they're very useful quantity, X, Y, and Z, right? It's just a way to label things in nature.
Okay.
But yeah, there is this point of view that gauge symmetry are actually not physical at all. I mean, they're just a redundancy of nature. But it's very convenient redundancy. But in principle, yeah, you could formulate everything without gauge symmetry. But
okay, more questions for Christophe? Yes.
Here you suppose all particles are or spin 0 or spin 1/2. You could have like mixed spin 1/2 and spin 0 and evaluate different cases.
I mean, just two extremal case. I mean, just to show you the difference. But yeah, you could construct different hypotheses. And, yeah, indeed.
Okay, so let's thank Christophe for this nice lecture. And so we have a coffee break. The coffee break is upstairs in the mezzanine. And we come back at 11 for the second lecture of the day. And for the Q&A, if you arrived a little late, we're going to introduce ourselves during the first Q&A session, okay? So thank you.